So in the last video I talked about, hey, hold up. In the last video I talked about these volumes of solids between solids. So the volume of the solid that's kind of weird. The volume between the solids that are created by this isn't it the volume of this entire big solid, which is this, minus the volume of the inner solid, which is a different function. Notice this has to be on top. The volume of the inner solid. Isn't that the distance? Isn't that the volume? And then we put a parentheses dx. I know you can factor out the pi. It makes the formula look much better. So we can factor out the pi and make the formula much better. But this is the idea. So the next concept is arc length. I'm gonna call it the length of a curve, so people can relate to it more, I guess. Because it really is arc length, but more people are not gonna care and think it's just a circle and the arc length. But this is area of a curve, and it's another integration application. It's one of those other ones, but so let's talk about arc length. So if I have a curve, I'm going to say, well, how long is this curve? How long is it? And people are going to say, well, it's this. Isn't it just this right here? Is that the length of the curve? No. It's not. Why would you think it is? See, this curve can be kind of stretched out like a string, and then you can find it, right? So what is the actual length of this curve that is modeled by a function? Ooh. Well, let's take a little section of this curve. Just a little section. And if we take the little section of this arc, we can think about two different things. We can say, well, what if I wanted to find the length of this arc? And it's not a circular arc, this is just a curve. And I want to use this and these 2 points. And I want to kind of approximate it by this little secant line. This segment right here. And of course, this is some delta x, and this is some delta y, right? So what is the length of my segment? Well, the length of my segment is the square root of these values, right? My delta y love. Isn't that right? Isn't that the length? Okay. But we could do it in more technical terms. We can do this in more technical terms. We can say, okay, let's imagine this being a point. This is x sub k minus 1, comma y sub k minus 1, right? This is the k, that's the before the point, sorry. So this segment length, and let me draw it bigger. This segment length from this point to this point could be x sub 1, right? Comma y sub 1. This could be x sub 2 minus y sub 2, right? But the point is figuring out the length. That's not really going to make an accurate representation of the length, right? How can we make this more accurate? So the length of this curve is what? The square root of x sub 1 squared, or the difference, sorry. So the length, this arc right here, the approximate length, this approximate length of this curve is a bad approximation, but we can still do it. Alright, this is what it is. Well, what if we can make this more better approximation? So what if I did this? What if I added 3 points, one in the middle? I'm going to change this to 3. And this is x sub 2 comma y sub 2. So if I did this segment, and then this segment. And now the length would be approximately this entire thing plus, so it would be that, right? Yeah. Plus 1 with x sub 3 minus x sub 2 squared plus y sub 3 minus y sub 2 squared. There you go. That would be the length, right? And this is a more accurate representation of the length of the curve. More accurate. Now we can get more accurate. So if I did this, and I would make a bunch of points, just a bunch of points, from here to there, 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 from here to there. Notice how you can't even see the difference. These are the points, and I'm going to make a segment out of each of these points. Remember? Notice how accurate this results in the length, the actual length of this curve. It makes it very accurate. But this is what? This is going to be what? The first points, right? X sub 1, y sub 1, x sub 2, y sub 2, all the way up to x sub n, x sub, or y sub n. So we're saying that the length is approximately equal to the length of the sum of the length of these segments. So you would put this down. Right? That's what you would put down. You would say we're just adding up all these lengths. You're adding up all these lengths. And what does this result into? Into a summation. So we're saying this length of the curve is approximately equal to the summation from k equals 1 to n of the square root of x sub what? K minus x sub k minus 1 plus y sub k minus y sub k minus 1. And if we're starting at 0, it's kind of the same thing, right? If this is going to be equal to 1, it's going to be the first point, 0. So if we really want to change this, change it into not the 0th point, the first point, if we want that to be 1, which we do, right? So isn't that our kind of a thing, right? That's our thing. Well, here's what we end up doing. We end up changing this a little bit more. So this is now the summation from k equals 1 to n. I'll make this a little bit smaller. This is the delta x sub k squared plus the delta y sub k squared. So we kind of changed it a little bit more to kind of see it better. Now, because we changed it, we gotta do some more work with it. So I'm gonna erase it so I need more room. I'm gonna kind of erase the geometry section. So we had the summation from k equals 1 to n. Notice this is an approximation. And we're squaring all these. Right? We're adding the lengths of the segments, right? That's approximating the length of my curve. Now, there's something cool that we can do. Something very cool we're going to make out of this. So we're going to multiply this. I'm going to multiply and divide by something, which is going to make it stay the same, right? It's going to be the same something that I'm going to divide and multiply by. So I'm going to keep the delta x sub k squared here, but I'm going to do this. I'm going to multiply by delta x sub k squared and then divide by delta x sub k squared. See what I did? I multiplied and divided by the same thing, meaning I'm just multiplying by 1. Basically, I'm not really affecting this at all. So let's go ahead and change it. A little bit more. This is delta x sub k squared plus the delta y over the delta x sub k squared. We can pull that out, can we? We factor out a delta x, right? So I'm going to do that right here. We can factor out a delta x squared, a delta x sub k squared, and we can leave a 1 plus delta y sub k over delta x sub k squared. This leaves us off with the summation from k equals 1 to n of what? The square root of 1 plus delta y sub k over delta x sub k squared. I'm going to put that down, times delta x sub k, which means kind of the same thing as delta x. It's the same thing, because we're assuming that it's all equal. When you're doing the normal partition, you're saying the rectangles don't have to be the same, right? When we put a normal partition. And that's why we put k's here. If we put n approaches infinity, then we put no k's. So, here's what we kind of end up. Here's what we kind of end up with. Because we have something called the mean value theorem, right? We have a mean value theorem. Where I have this arc, and this are the same. The slope of that equals the slope of the prime, right? Well, I'm going to smush it down. I'm going to smush them down, and you gotta remember the mean value theorem. Look it up in a notebook or something. The mean value theorem says, hey, my rate of change could be my instantaneous rate of change on an interval if the function's differentiable, right? Well, what we're going to do is we're going to let the segments so small. We're going to let the segments, we're going to let hold up. I'm going to erase it a little bit more, so write that down, make sure you have it all. I always keep the top thing the previous thing that we did on. So don't worry. So what do we come up with? The length of the curve is approximately the summation from k equals 1 to n of the square root of 1 plus delta x over delta y sub k's. And we're squaring that times the delta x sub k. So what we're doing here is we're saying, wait a second. The mean value theorem states that if my function's continuous, and we have to make it continuous, and if it's differentiable, we have to make it differentiable to find arc length, right? Then, on that interval, the average rate of change equals the instantaneous rate of change at some value c. But since we're making, and if we do this, if we make the limit as the norm of the partition, meaning if every single segment, if the biggest segment in our entire curve that we make out of approaches 0, all the other segments are going to be basically 0. So that means we're going to have an infinite many segments left over. So if we have the normal partition approach 0 of this entire statement, and if you like to use n approaches infinity, just put n approaches infinity and remove the case. It'll be good. I'll do that later. So what's happening is, hey, mean value theorem says, hey, I already told you what it says, right? So we're making the smallest the biggest segment approach 0. Therefore, if we have this in our smallest segment right here, then the interval from here literally equals the instantaneous rate of change. You can't even see it, but if we make a small enough segment, so that interval is equal to the instantaneous rate of change. It's equaling the instantaneous rate of change, which means we're getting the derivative. So this delta x and the delta y hold up. This is delta y, remember? Sorry. I made a small mistake. There. Change that to dy or delta x, delta y over delta x. So this small, there's going to be such a small delta y over delta x that it becomes dy dx. It becomes the derivative because it's so small, and the mean value theorem will, if you're somewhere in that interval, is going to be f prime because your interval is so infinitely small that c becomes the only point that you have, and you're using the segment almost for 1 point. You're letting it approach 0. Therefore, mean value is like, okay, well then might as well be the derivative because you're the only segment in that place, right? So what I'm trying to say is let's just replace this with the derivative because we're making our segments so small that mean value theorem just says, well, your average rate of change is going to be just the derivative because it's so precise. So this is 1 plus f prime of some x sub k delta x sub k. So that's what it is. Oh, wait. Let's do a substitution here. Let's do a substitution. If we have g of x sub k equals the square the square root of 1 plus f prime. Oh, it's dy dx squared. That's right, d squared. If it's f prime of x sub k squared, just let that be. We can change this. This is equal to. From now on, this is equal to. That's approximate, that's equal. The limit as the norm of the partition approaches 0 of the summation from k equals 1 to n of, well, we substituted g sub x sub k. Now delta x sub k. I'm going to say, hey, might as well, let's make all the rectangles, when I mean rectangles, for this kind of thing. Might as well. Well, what is this? Well, that's the definition of the definite integral. This is the definition of the definite interval, right? It's just g of x now. dx. Wait, let's make the substitution back. What's g of x? It's 1 plus, is the square root of 1 plus f prime of x squared. Oh, let's substitute it in. I'll put it here. The length of the curve is the integral from a to b of the square root of 1 plus f prime of x squared dx. That right there is the length of the curve. That took almost half an hour to show. Now, I'm not going to really do problems with this because we know. So this is length of a curve. That's length of curve. You know, through this idea, we can come up with surface area. I'm not going to show you the proof for surface area, but it kind of takes the length and revolves it. So the surface area of the volume that is revolved about the x-axis is going to be the integral from a to b. So the integral from a to b of 2 pi times, let's see, okay, 2 pi times f of x times the square root of f of 1 plus f. So these are big integrals now. These are going to be harder problems, obviously. There's going to be only a select few integrals that you can do with this application stuff, and you'll learn more about it. So all of x is just f of x is the distance. Okay, so that is it. So that's it. That's the surface area of the volume. So this is the surface area of the solid that is revolving. So it would be the surface area of something like this, you know? Some of this vase stuff. That's the surface area. Oh, that's kind of nasty, but it would be the surface area of a solid of revolution, the one that we did last section. So that would be it. And that's all. I'm not going to do any examples. You can plug in your function yourself. It's not that difficult. You'll be given a function, you'll be given, and you'll find the length of the curve or the surface area of a solid of revolution. And there you go. If you want, when they tell you from y, if there's revolving about the y, you would replace with g of y and g prime of y, and from c to d. That's all you have to do, and that's a dy. If you want to do it for the other direction, and that's it. That's arc length right there.